We will use Easy Tolerance Analysis extension, also referred to as EasyTA, to study the gap between the wheel and the bushing. This is an example of a tolerance analysis to study the gap at the largest possible width. The gap is maximized by pushing the axle supports out away from the center line of the caster wheel. When we complete the analysis, we find the range of the results of the gap. As we open our active session of Creo, we find the EasyTA application under the Applications tab. We choose the new Stack Up tool and follow the menu or the directions in the message log. We find the gap between the wheel and the bushing in the model and choose the Start feature on the wheel, then the End feature on the bushing. A direction is set automatically if either of the features we choose are planes. As we locate where the dimensions will appear in the model, we are prompted to complete the part loop by selecting components and defining how they touch. Part loop paths are found using the assembly constraints from your model. Select a path that represents the part loop you want to use. You select if the available paths do not represent the part loop you need. We finish the stack up in just 5 easy clicks. Dimensions appear in the model and a table appears that lists the stack up components, parts, and dimensions. Icons that look like chain links indicate dimensions that are linked to annotations in the part models. Click on the icon to break the link to explore ways to improve the results. Tolerances are expressed as symmetric, plus minus, limits, or geometric. When updating a geometric tolerance, choose from a list of geometric characteristics, revise the tolerance value, choose a datum reference, and when applicable, adjust the material and boundary modifiers. The table has lines to address the assembly shift between fasteners and holes. Our options are to choose a floating bias or a bias that will maximize or minimize the gap. Our analysis results are found at the bottom of the table. In this area, we can rename the stack up. Here we can change the objectives to express how much variation is allowed and how the objective relates to the results. This relationship is expressed as symmetric, plus minus, limits, upper limit or lower limit. Here you can choose a worst case, RSS, or generalized statistical analysis. Statistical results are expressed as CPK, sigma, percent yield, or defects per million opportunities. In the table, we can change the CP values from a default value for the model to a distinct value at the part level, or the dimension levels to reflect your manufacturing process capabilities. We can see how our results relate to our objectives in the Results tab. Let's compare the results in the Results tab and the results from the spreadsheet analysis we saw earlier. We see the values between the EasyTA and the spreadsheet results match. We learn what causes variation in our stack up in the Contributions tab. The highest contributors focus us where to improve our design functionally, while the lowest contributors present opportunities to reduce manufacturing costs by opening tolerances. We will take a snapshot of the model with stack up dimensions. This image will be used in a report we will create. Now we want to study the overall height of the assembly. Using the new Stack Up tool, we choose the Start and End features and locate the dimensions. This time, instead of using the assembly constraints, we manually select the part loop. When we choose the Select option, the component associated with the Start feature becomes transparent. We select the component adjacent to the transparent component or follow the directions in the message log to make our selection. As we select all the components in the part loop, the components become transparent. Next, we indicate how the components touch by selecting the mating features between the components. You will see a pair of components to focus your selections. Choose the feature on the solid component that mates with the transparent component or follow the directions in the message log. Once we complete the loop, our dimensions appear in the model along with the stack up details table. Because our stack up includes a cylindrical surface, we need to make sure we have the correct starting and end points. In the stack up table, we will select the start and end points that reflect what we want to study. We change the name of the stack up. Next, we modify our objectives. Now we will take a snapshot of the stack up as we move to the summary page. On the summary page, we can see a list of all the stack ups in the model. In the Results tab, we see how many stack-ups meet our objectives. In the Contributions tab, we learn what contributes to variation for all stack-ups in the model. For the summary section of the report, we will take a snapshot of the model. And now we will select the Generate Report button. Now we see a report that includes all the model snapshot images for the summary section and all the sections for the individual stack-ups. We see a summary of the stack-ups. For each stack-up, we see the details. With the details, we see a visual of how the results relate to objectives. And finally, we see a list of contributions. If you have any questions about EasyTA, please contact your PTC sales rep or Sigmetrics to find out more.